rho c dt dt equals negative divergence of Q. Okay, hello and welcome to our video. I'm going to start off today with explaining the heat equation and eventually how that can become discrete. To start off, we'll start with the amount of energy, of total heat energy in a region. This is defined as the integral of rho c, both with rho being density and c being thermal conductivity of a region times temperature throughout the region. So essentially like adding up each little bit of heat throughout a region. To take the rate of change of this, we simply take the derivative of it over time. Now, due to the law of conservation of energy, this value, the rate of change of heat in a region, is equivalent to the amount of heat leaving the surface of that region. So it's the amount of heat that is normal to the surface that is leaving it, the negative sign there. And that's just over the boundary of the region. Now, because of the divergence theorem, as I'm sure you all remember, this is equivalent to the amount of divergence in a region, the negative amount of divergence in a region. Okay, now with a little bit of rearranging to that equation, we can come to the equation, the integral of the region of this first equation that we have here, brought the derivative to the inside, plus the divergence of the heat, just with the dV thing, in the both of them, equals 0, just with a little bit of, addition. And now because this region is just arbitrary, it's kind of any region that we want, and it's true for all regions, we can just get rid of it. And that means that this is true. Rho c d temperature over dt equals the divergence of heat flow. Okay, so we have our equation from before, and we also have this new fun equation called Fourier's law, which is that the rate of change of Q is equal to the negative grad of T. So we do a little fun subbing in, and we get our previous left-hand equation from before, and now it's equal to the div grad of T. Now you might be saying, well, that T is temperature, but we want heat. Well, if you recall, heat is equal to rho c T. Yeah? I like the sound effect. So we can take this rho c of T and we can say that that is equal to du dt. And we can also just say that this rho c kind of thing is now just a constant. It's a constant k of proportionality. And so now over here we have k of this del operator squared, which is just a fancy way of writing div grad of u. And this is the heat equation. First frame. Okay, so now you remember our nice lovely heat equation formula from before. Now if you're wondering, this is essentially stating that the rate of change of heat over time is equal to the curvature of heat over space. So if you imagine a rectangle that has some kind of heat distribution, let's say it goes low and then up high, that shape that the curvature creates will be equal to the rate of change of u as it levels back off. Okay, so now if we want to look at this in one dimension, we can just take the partial derivative of u in terms of t and the partial derivative of u, or the second partial derivative of u in terms of x times a constant k. Now we have this in one dimension, but for our function we want to look at it in discrete terms. So we want to look at it as though we have points in our line that are exchanging heat back and forth in a discrete pattern rather than a continuous function like this. To take this into a discrete form, you take the u at one point I in the future and take the difference between that and the point of u that you're at in this present time. Then you divide that by the time difference between them. And then that is equal to the k, whatever constant you have, times the u of the future space, so like the u of the next space over, plus the u of the previous space, minus 2 times the u of the current space, all divided by delta x squared.